1/8 of an inch. That is the gap between two pieces of steel under every freight train that clicks through your town. You have heard that sound your entire life. At crossings, on overpasses, through open windows on summer nights. That rhythmic pulse, steel on steel, repeating every 39 feet for the length of the train. Most people assume the sound is just what trains sound like. That click is the sound of a wheel dropping into a gap left on purpose between two rail ends bolted together with a device patented in 1847. The bolted fishplate joint is the oldest operating technology in the American freight system. It predates the telephone, the light bulb, and the automobile. And as of today, it is holding weight under trains carrying chlorine, crude oil, and grain across 50,000 miles of American track. Have you ever listened to that sound and wondered where it comes from? Tell us in the comments. This is what American Ironworks covers. Subscribe so you do not miss what comes next. In 1842, an English engineer named William Bridges Adams had a problem with the way railroads joined their tracks. The standard method was the scarf joint. Each rail end was cut at a diagonal, halved in thickness, and overlapped with the next rail. The splice looked clean. The physics were terrible. The rail was thinnest at the exact point where the stress was greatest. Every wheel that crossed the joint hammered the weakest spot in the entire track structure. Adams watched rails crack at the splice under routine traffic. He designed a flat steel plate that clamped to the outside of both rail ends and bridged the gap without thinning the rail at all. He named it after the curved wooden bars that sailors bolted to cracked ship masts. A fishplate. In 1844, the Eastern Counties Railway in England tested his plate as a wedge between rail ends. In 1847, Adams and Robert Richardson patented the full design. 2 years later, a railway engineer named James Samuel added bolts through the plate and the rail web, creating the version that would spread across the world. That was 1849. The design has not fundamentally changed since. 2 steel bars sit against the rail web, one on each side. 4 or 6 bolts pass through aligned holes in the bars and the rail. The bolts alternate direction, 3 facing inward and 3 facing outward. That alternation is deliberate. If a derailed wheel strikes the joint, the opposing bolt directions prevent a single shearing force from snapping all 6 at once and separating the rails entirely. Between the 2 rail ends, a gap of 1/8 of an inch. That gap is the entire point. Steel expands when it heats up. A rail sitting in direct sun on a July afternoon in Nebraska can reach 140 degrees Fahrenheit. If the rail has no room to grow, it pushes sideways and the track buckles into an S-curve that can derail a loaded train. The gap prevents this. Every 39 feet, the rail ends, the gap absorbs the expansion, and the next rail section begins. That is the click. The wheel drops into the gap, crosses to the next rail, and the process repeats roughly 270 times per mile. The gap does something else the railroad never planned for. When a 286,000-pound loaded freight car crosses a fish-plated joint, the weight of the wheel pushes the departing rail end down slightly. Engineers call this pumping. The rail tips into the gap under the load, then springs back as the wheel transfers to the next section. A train with 100 cars crossing a single joint produces 400 pump cycles in under 2 minutes, 1 for each wheel. That motion opens a path for rainwater to seep beneath the ties and erode the crushed stone ballast holding the track in position. Over months, the pumping deepens, the ballast loosens, and the joint sags lower than the solid rail on either side of it. Maintenance crews have to resurface the ballast and retighten the bolts at those locations more than anywhere else on the line. The fishplate joint is the weakest link in the track by design. It always has been. The 39-foot rail length made it weaker still. That dimension was not chosen by an engineer. It was set by a shipping constraint. In the 1800s, railroads transported new rail from the steel mill to the construction site on 40-foot gondola cars. The longest piece of steel that fit inside a 40-foot car was 39 feet. Steel mills built their rolling equipment around that dimension. Transport crews loaded to it. Track gangs planned their shifts around it. The number locked in before anyone understood what it meant for the track. Shorter rails mean more joints. More joints mean more bolt holes. The FRA classifies bolt holes as the most significant structural weakness in jointed track because fatigue cracks start at the stress concentration around the drilled hole and propagate outward through the rail web. Between 1992 and 2002, track failures involving rail, joint bars, and anchoring caused approximately 2,700 derailments across the United States. A different rail length would have meant fewer joints, fewer holes, fewer cracks. But changing the standard would require changing the mill, the car, and the crew all at once. Nobody changed it. 39 feet became permanent, and the industry spent the next century trying to eliminate the consequences. In the 1950s, they found a way. The solution worked so well that it created a problem the joints never had. Continuous welded rail changed the physics of American railroading. Welding plants took standard 39-foot rails and fused them into quarter-mile ribbons, 1,440 feet of unbroken steel. Some plants used flash-butt welding, running heavy electrical current through the touching ends of two rails until the metal fused at the contact point. Others used thermite welding, a chemical reaction that generates enough heat to melt steel directly at the joint site. Special rail trains carried the finished ribbons to the work site. These trains are among the longest dedicated work consists on the railroad, loaded with dozens of quarter-mile steel ribbons stacked on roller cars. At the site, the train pulls forward at walking speed, while the bottom ribbon slides off the rollers and drops onto the ties below. One pass lays a quarter-mile of jointless rail. Field crews then welded the quarter-mile ribbons together into continuous runs stretching 5, 10, 20 miles without a single joint. For railroads that could not justify full replacement, a cheaper option existed. Welding contractors cut out the 6-inch sections of rail containing the bolt holes, slid the remaining rail forward to close the gaps, and flash-butt welded the seams in place. This crop and weld method converted bolted rail into continuous welded rail for roughly 2/3 the cost of installing new steel. The clicks vanished, the bolt hole cracks vanished, the pumping at rail ends, the eroded ballast, the loose fish plates rattling under traffic, all gone with the gap. Welded rail lasts roughly 1 billion gross tons of traffic before needing replacement. Jointed rail lasts 600 million. The savings in maintenance alone justified the conversion. By the end of the 20th century, virtually every Class 1 main line running above 25 miles per hour had been converted. The rides got smoother, the trains got faster, and the system stopped breathing. Without the gap, the expanding steel has nowhere to go. Continuous welded rail is installed at what engineers call the stress-free temperature. That is the rail temperature at which the steel carries zero internal force, neither pushing outward nor pulling inward. In the United States, the stress-free temperature ranges from 95 to 109 degrees Fahrenheit. Below that temperature, the rail is in tension, trying to contract. Above it, the rail is in compression, trying to expand. A 100-meter section of welded rail that climbs 50 degrees Celsius above its neutral temperature wants to grow by 55 millimeters. It cannot. Clips and ballast hold it rigid. When the compressive force exceeds the lateral resistance of the track structure, the rail does not bend gradually. It snaps sideways, sometimes in less than a second, into an S-curve that can throw a loaded freight car off the track. Railroad workers call it a sun kink. The Federal Railroad Administration calls it a thermal misalignment. Over the last 4 decades, sun kinks have caused more than 2,100 train derailments in the United States. That is an average of 50 per year. Since 2019 alone, track buckle derailments have caused roughly $26 million in reported damage. The gap between a delivered freight car and a ruptured tanker of Bakken crude is the absence of the gap in the rail. The old joints absorbed expansion automatically. The welded rail fights it. How wide is the margin between a stable track and one that buckles? About 20 degrees. In extreme cold, the opposite happens. Welded rail contracts under tensile stress, and the steel can crack clean through. Maintenance crews in North Dakota and Montana respond to fractured rail in winter by laying fire snakes along the track. A fire snake is a strip of flammable material wrapped in a plastic casing, roughly the width of a garden hose and several feet long. At 2 in the morning, with the air temperature at -20 degrees Fahrenheit, a track worker walks to the fractured joint, lays the fire snake against the contracted rail, and lights it. The flame runs along the length of the strip. The radiant heat warms the steel enough to expand it back into contact with the adjacent section and restore the electrical signal circuit that detects passing trains. On a freight network worth $80 billion a year, the fix for a cracked rail in January is fire, applied by hand in the dark. In June of 2026, Union Pacific announced a different approach for summer. High rail trucks with spray rigs now apply white paint to both sides of the rail in high heat sections across the railroad's 32,000-mile network. The white surface reflects sunlight and lowers rail temperature by approximately 20 degrees Fahrenheit. Union Pacific's Chief Safety Officer, Rod Doer, said the railroad took a page from road striping. The company reported its lowest full-year derailment rate in history in 2025, a 19% improvement year-over-year. The Italians had been painting their rails for years before Union Pacific tried it in North America. The welded rail is stronger, quieter, and longer-lasting than the jointed rail it replaced. It also requires constant monitoring, periodic de-stressing by specialized crews, and now a coat of white paint to survive the same heat the 1/8-inch gap absorbed for free since 1849. The old joints survive across a third of the American rail network, and the people maintaining them are the most invisible workforce in freight. 600 short-line railroads operate approximately 50,000 miles of track in 49 states. That is 29% of the national freight system. These railroads inherited their track from Class 1 carriers who decided the traffic volume no longer justified the maintenance cost. Much of that inherited track is jointed rail, bolted together with fish plates and tightened by hand. Short-line railroads reinvest a minimum of 25% of their annual revenue into track rehabilitation. That reinvestment rate is higher than almost any other industry in the country. The workers on those lines walk the track and inspect bolt holes by eye and by hand, looking for hairline cracks that could fail under the next train. They retighten joint bars that loosen under thermal cycling, torquing the same bolts their predecessors torqued on the same rail their predecessors laid. Some of this rail has been in the ground for 40 years. The fish plates holding it together are the only thing standing between a functioning branch line and a derailment carrying anhydrous ammonia through a town of 800 people. These workers are the reason freight reaches 10,000 customers in communities that Class 1 railroads decided were not worth the cost. The global market for jointed rail is not shrinking. It is growing at 8.5% per year, driven by demand in regions where traffic does not justify the cost of welding. The technology the industry declared obsolete on its main lines is expanding on its margins. The next time you hear that clicking sound at a crossing, listen to it differently. That is not the sound of something outdated. That is the sound of a 1/8-inch gap doing exactly what it was designed to do 177 years ago. Absorbing the heat, releasing the pressure, letting the steel breathe. The welded rail is better by every measure except one. It cannot do that. 39 feet of steel, a pair of fish plates, and 6 bolts. The oldest working technology in American freight is out there tonight, clicking under the weight. And the newest technology on the railroad is a coat of white paint, trying to solve the problem the click already solved. Subscribe to American Iron Works for more of the engineering, hiding under the freight system you see every day.